All this artificial intelligence that's completely changing our world, well, it runs hot. I mean, incredibly, unbelievably hot. And that heat is actually one of the biggest roadblocks to the future of computing. So, just how hot are we talking about here? We're talking about a single, high-performance AI chip kicking out 1,000 watts of heat. To put that in perspective, that's like taking a small space heater and cramming it onto a tiny piece of silicon about the size of your palm. As you can imagine, the old ways of cooling things down are really starting to struggle with that. So yeah, that is the billion-dollar question, isn't it? How on earth do you manage that much concentrated heat to keep this whole AI revolution from, well, literally melting down? The answer, it turns out, is less about brute force and more about some really elegant physics. Okay, so let's dive into how this works. And the best way to get it is with a super simple analogy. Just think about the difference between taking a cold shower to cool down versus what happens when you boil a pot of water on the stove. That difference right there, that's the key to understanding the old way versus the new way of cooling these monster chips. See, when you really get down to it, there are only two fundamental ways you can pull heat away from something. You can either make a cool thing warmer, or you can make it completely change its state, like turning a liquid into a gas. And that difference, as you're about to see, is everything. Let's break this down. Traditional cooling is our cold shower. You run cool water over a hot chip, the water gets a bit warmer, and it carries some heat away. Simple enough. But with a 1,000-watt chip, you'd basically need a fire hose of water to keep up, and it becomes super inefficient. Now, the new method, two-phase cooling, is the boiling water. With this, a special liquid doesn't just get warmer when it touches the hot chip, it instantly boils and turns into vapor. And here is the secret sauce behind it all, a scientific principle called latent heat. When a liquid turns into a gas, it has to absorb an absolutely enormous amount of energy just to make that change happen. But here's the wild part. It absorbs all that energy without its own temperature going up. So you're not just warming up a liquid by a few degrees, you are harnessing the awesome power of a phase change to soak up heat like a sponge. And the difference in just how well this works is, well, it's staggering. Look at this. If we say regular old air cooling has a power of 1, then the cold shower method, just warming of water, is already almost 4,000 times more effective. That's a big jump. But now look at the boiling method with a special refrigerant. We're not talking 4,000. We're talking 150,000 times more effective than air. It's not an improvement, it's a completely different universe of cooling power. Okay, so that's the science behind it. But how does this incredible principle actually get put to work inside a server rack? Well, it's all part of a really clever, self-contained cycle. It's basically a 4-step dance. First, that special liquid is pumped to the hot chip, where it instantly boils, turning to vapor and absorbing all that intense heat. Second, that mixture of liquid and vapor flows away. Third, it reaches a condenser where the hot vapor cools down, turns back into a liquid, and releases all the heat it was carrying. And finally, that cooled liquid is pumped right back to the chip to start the whole thing over. It's a perfect loop. Now, a huge side benefit of this whole boiling process is temperature stability. See, a liquid boils at a constant temperature. And what that means is the entire surface of that very complex AI chip is kept at a perfectly uniform temperature. No dangerous hotspots, no weak points that could cause errors, just pure, even cooling. I absolutely love this analogy. It just hits the nail on the head. It really is like giving the chip its own personal sauna. It gets to sweat out all that heat through evaporation, which keeps its temperature perfectly regulated no matter how hard it's working. And let's just hammer home how efficient this is. For the exact same amount of liquid, this boiling process absorbs over 40 times more heat energy than just warming up water. 40 times! It's not just a little bit better, it's in a whole different league of power. So what does all that efficiency mean in the real world? It means the system only needs to pump about 1/10 the amount of liquid compared to a traditional water cooling setup to get the job done. Think about that. Less liquid means smaller pumps, which means less energy being wasted just on the cooling system itself. And here is a major bonus, especially for the people managing these incredibly expensive data centers: safety. The liquid they use is called a dielectric fluid. All that means is that it doesn't conduct electricity at all. So if a traditional water cooler springs a leak, it's a catastrophic short circuit, game over. But if this stuff spills onto a multi-thousand-dollar server, it's completely harmless. It just evaporates without damaging a single thing. Now, As absolutely perfect as this technology sounds, it's not without its challenges. Getting this to work flawlessly in the real world, 24/7, requires some seriously clever engineering. There are three main hurdles to clear. The first is something called dry out. You have to make sure you're supplying liquid fast enough so it doesn't all boil away, kind of like a pot boiling dry on the stove. That would cause the chip to overheat instantly. The second is flow balance, making sure every single chip in a giant server rack gets the exact right amount of coolant. And finally, there were some environmental concerns with the first generation of these fluids. But the good news is the industry is already way ahead on that last point. Some of the early coolants had PFS, also known as forever chemicals, which aren't great for the environment. So those are being phased out and replaced by a whole new generation of fluids that are not only eco-friendly, but also non-flammable, which adds yet another layer of safety to the whole system. So after all that, what's the big takeaway? Why does a new way to cool computer chips matter so much? It's because the ambition of AI, what we want it to achieve, is directly tied to the raw power of the hardware it runs on. And that's exactly why this two-phase cooling is being called the ultimate weapon for the AI era. To build bigger, faster, and smarter AI, we need chips that are more and more powerful. And to keep those chips from literally burning up, we need a cooling revolution. And it turns out that revolution might just be as simple and as incredibly powerful as boiling water.